For gas, liquids and gases, you just have beta. Yeah, for liquids. So we're going to focus on this chapter on liquids and solids, because gas expansion depends on, are you expanding it isothermally, isovolumically, or isobarically? So that's a different concept. For liquids and gases, we don't have to worry about that. Isobaric, isovolumic, isothermal, you know. For liquids, delta V is going to equal what? It's just going to be beta V initial delta T, similar looking to the solid three-dimensional. But for solid, beta is 3 alpha. You see? But for liquid, beta is just a number. So beta V initial delta T. And then these are the beta of different materials. Ethyl alcohol, 11, let's see, what kind of number is that? Ethyl alcohol, 1120 times 10 to the minus 6. So it's going to be more like 1.12 times 10 to the minus 3. See, that's bigger than the solids, right? Remember, solids were 10 to the minus 6. And even if you multiply them by 3, it's still 10 to the minus 6. So a liquid responds more to a change in temperature, which makes sense because liquids are less loosely attached to each other, you see. And then beta of mercury, okay. If you go back 2 spaces, 1, 2, this is going to be 10 to the minus 4, right? Okay, so mercury expands less than the alcohol. Well, that makes sense because mercury is more like solid, very dense. See, alcohol evaporates easily and also should expand more than mercury. Yeah. So that usually when you look at numbers, again, they should always be making sense. Glass, I guess they're, I'm assuming, oh no, glass, they're doing solid glass. So 3 times the alpha. You see, 3 times the alpha, 3 alpha, and then they're taking their alpha, it seems like they're solving a problem there or something. Liquids in glass thermometer. The alcohol is colored red to look like wine. Cars that coolant overflow tanks. Coefficient of linear expansion, coefficient of volume thermal expansion. You see here, particularly for water, the volume expansion of water is very temperature dependent. So at 1 Celsius, the volume beta of water is -50. So actually when you increase the temperature of water from above 1, the volume actually contracts. And at 4 degrees Celsius, it reaches the most densest water, it's 4 degrees Celsius. Because it contracts from 0 to 4. Without that, life would not exist on Earth. Because you can't have 0-degree water be the densest water for life to exist. Right? You have to have 4-degree water for life to exist. Because you want the densest water, which is going to sink to the bottom. You don't want it to be 0 degrees Celsius water, because then the lakes will freeze over. Right? The 0-degree water will sink, and the bottom of the ocean might freeze. And then they will keep sinking and the whole ocean might freeze. So that's very important for life to exist. Water has a property that it's negative beta up to 4. Then it's 0. Then after that, it responds very, very fast to changes in temperature. And the beta keeps increasing. You see? Something unusual like that, fact, is so important for the existence of life. Okay, so now how are we going to do? Let's do like an example. We have a solid ball. So let's say this has a radius of 2.41 millimeters, and then you have a disc here. So you're trying to put the rod through the disc, right?
Okay, now we're here, we're going to illustrate the principle. What happens when the ring, and the ball fits nicely through the ring, okay? What happens when I warm the ball? What's going to happen? Okay? So I'm going to exert some heat through the ball. The ball should expand, right? The volume of the ball should expand. Now the ring is kept at the same temperature. Okay, a little bit harder. Doesn't go through. Let me heat it up even more. Well, now it's even the beginning portion doesn't even go through. You see? Yeah. And now it's getting even harder to go through, right? Now what happens if I also heat the ring? Is the hole going to expand? Now what's going to happen is it's going to expand, right? Is the hole going to get bigger? Because the metal is going to get bigger, right? Does the hole get bigger or does the hole get smaller? That's often a question that's asked in physics class. When the ring gets heated up, because the material gets thicker, right? It gets thicker, 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 thicker. So does the hole get smaller or bigger? The answer is it gets bigger, okay? So if I heat this up, heat that up, okay?
Yeah, you
It
see
can
that?
fit through, right?
So what if we make it as general as possible? Make this like a little bit smaller, make that a little bit bigger. Let's say the inner radius of this. That's all that matters, right? R2, and this is the radius of the ball. So we'll call this R1 is the radius of the inner radius of the out of this one. Let's say it's 2.43. And let's make the inside one a material that has a bigger alpha, right? So that would be, let's say, let's make this outer one steel, and let's make this aluminum. steel, I think, had something like 11 times 10 to the minus 6, and aluminum was like 24 times 10 to the minus 6, right? So if the initial temperature of both of them, T initial is 24 Celsius, how much should I heat both? Let's assume I'm heating both of them. How much should I heat both so that the ball barely fits into the ring, right? The whole of the, as we saw in the video, the whole of this one is also gonna get bigger, right? So for this one, since it's a spherical ball, the volume changes as 3 times alpha, right? So it's gonna be delta V is gonna be 3 alpha V initial delta T, right? So delta V is going to be 3 times 24 times 10 to the minus 6, 4/3 pi r 1 r whole cubed, which is going to be delta T. But then delta V is going to be what? V initial plus V final minus V initial, right? So V final minus V initial, and then V final is equal to V initial, which goes over there, 4/3 pi r whole cubed plus 3 times 24 times 10 to the minus 6 times 4/3 r pi r whole cubed delta T. In other words, this is delta V, right? If I add delta V to V initial, that gives me V final, right? And then V final is going to be 4/3 pi r final cubed. So I think the 4/3 pi just cancels. And then our final cube is going to be what? I can factor out the r ball cube. 1 plus 3 times that is going to be 72 times 10 to the minus 6 delta T. Then I can take the cube root of that. So that means depending on delta T, that will be a general equation that tells me the final radius of the ball. Cube root this, so our final is going to be r ball cube root of 1 plus 72 times 10 to the minus 6 delta T. So now I need some equation that tells me the final radius of the outside material. So since I don't care about the area of that one, how big the area gets, I'm only interested in the inner radius, right? So I can treat that like a linear problem. I can say the final radius here is equal to the initial radius plus delta L, the delta of the radius, right? So then our final is going to be R initial plus delta R is going to be R initial alpha delta T. So that one is more linear equation, right? So our final is going to be R initial 1 plus alpha delta T. And the alpha of that, since it's steel, is 11. So this definitely has a chance of catching up to that, right? So then our final is going to be our initial 2.43 So one is a linear equation and one is a cube root equation. So graphically it looks something like this. The radius of the spherical ball goes up like a cube root sphere, and the radius of the other one goes up slowly as a linear function. They might crisscross twice, as a cube root function looks like this. So I'm interested in this temperature. After that, if I heat it more, it can't go through, right? If the first crisscross. Okay, so then I set this equation equal to that. This one equal to this. So the radius of the ball, the spherical ball was 2.41, right? I can treat delta t like an x, right? And then that's equal to 2.43. Okay, now put that in solver and solve for x. $661.9. Ooh, that's a lot. Or the other answer is 78,899 Celsius. So remember that they can crisscross twice, right? So I'm interested in the 661.9. This is delta T. Okay, so if the problem is asking for delta T, you could say you should heat up both metals by 661 Celsius, right? But if it's asking for the final temperature of both metals, then that's just going to be its initial temperature plus delta T. So 24 plus 661.9, so 285.9. That's going to be the, 685.9, and that's going to be the final temperature of both metals. Now, if we weren't heating up the second metal also, if we were just heating up the ball would reach it quicker, right? So that graphically, it'd be like this guy just being straight. Right? So then it would be meeting it here. So what would happen? You wouldn't have this portion of it, you know? So let's see here. Oh, then it meets it only once, only one answer. Let's see, it just goes like that. So then that would be 348.6, okay? So in that case, delta T would be 348.6 degrees. So much easier, but it's still a lot hot. You have to really, really heat it in order for it not to go in. Okay, cool. So we'll continue this And then we're about to start chapter 20 Wednesday, which is going to be, so we'll do a little bit more example of this, and we'll start chapter 20, which is specific heat, heat of fusion, heat of vaporization, and also radiation, conduction, and first law of thermodynamics. A lot of topics in there. Okay.